Well, I'm very honored and happy to have Dr. Restrepo here from ORNL. We are very lucky to have scientists of his caliber just up the street, and we were hoping to have him here in person, but unfortunately, of course, due to some restrictions, we're doing it via Zoom. We hope at some point in the future to have you on campus, Dr. Restrepo. We would love that. Dr. Restrepo's path to section head of mathematics and computation at ORNL is a little bit windy. His early study of music and experience playing music professionally in high school led him to New York University, and he holds a BS in music from there. He also worked as a musician and a recording engineer in the New York City area. And when he got sick of that, he enrolled in Columbia University to study electrical engineering, working briefly at the Columbia-Princeton Electronic Music Laboratory, where he met Professor Cyril Harris and began studying engineering acoustics. He holds an MS degree in engineering acoustics from Penn State and a physics PhD from Penn State as well. Prior to becoming ORNL Mathematics and Computation section head, he has been a faculty member at Oregon State University and the University of Arizona. He also holds a joint faculty appointment in the math department at the University of Tennessee, Knoxville, and is an adjunct faculty in the mathematics department at Oregon State. His research focuses on climate variability, ocean dynamics, and problems at the intersection of statistical and deterministic mathematics. His success is a result of his multicultural background and diverse experiences. He has been recognized for his work multiple times, including as an ORISE Distinguished Postdoc Fellow at Argonne National Lab and a recipient of the DOE Early Career Award. So please help me welcome Dr. Restrepo to Maryville College.
Thank you for that introduction. That was very flattering, and I'm really pleased to meet you, at least virtually for now, but I definitely would like to be able to have the opportunity to meet all you guys, the students, everybody. And please call me Juan. That's what my students call me and everybody else does. And so what I thought I would do is essentially talk to you a little bit about climate, but what I'm going to do is I'm going to focus, comes with an anecdote. So I was asked by some members of Congress to come up with simple ways of demonstrating actually that climate change is real, and what sort of what can a mathematician say about climate change. And so first I got really esoteric and obtuse, but then I thought, okay, no, what I need to do is I can show this using fairly elementary and compelling methods. I don't know if I succeeded in Congress, but I did put together a presentation that I think makes the point quite clear. So the talk is really called Climate Changing, but is it changing in the way people think it is? So now I'm going to try to share my screen. Okay, this is a little fumbling here. I'm using a different computer. Okay. Okay, so hopefully everybody can see my screen now. Is the screen up?
Yes.
Okay, thank you. All right, and please do interrupt me if you have any questions or comments. I'm making the talk short enough so that we can accommodate plenty of questions. Uh-oh, okay, I'm using a different computer because I can't use the DOE computer. Okay, here we go. All right, so first of all, let me establish what scientists say about climate. And this comes from a national assessment on climate science. It's built upon lots and lots of researchers' work and lots of peer review results in climate. And basically it comes to four points. These have been updated slightly, but this is what they say, is that we're fairly certain, 95% certain, that human activities are responsible for global warming, at least for the industrial era. The second one is that carbon dioxide has been at an unprecedented level, not seen since, well, maybe almost 1 million years ago. Sea level is rising fast, and it's been faster in the last 40 years. And finally, over the last 2 decades, Greenland and Antarctic sheets have been melting at unprecedented rates. And we can add plenty of other things, but these are the 4 key findings, and they're backed up by pretty good science. And if you need some references to these, I can provide these for you. Now, the bad news is the following: is the IPCC, which is the International Panel on Climate Change, which is composed roughly about 10,000 scientists who get together once every, I forgot now, it is 6 years, 5 years, 6 years, and they release a report. What they do is they get together and they comb through all of the literature in climate science, peer-reviewed science, and they produce a fairly large document called the IPCC report, and they tell you what is the consensus, the scientific consensus. Now, what they're hoping is that we can limit global temperature increases to about 2 degrees Celsius since 1850 by 2100, but apparently the balance of basically greenhouse gases has made it much more difficult to reach that. And now what we need to do is reach 1.5 by then, which is a really tough challenge. And the reason we want to get to those levels is because at that level, then there's a runaway event. No one will tell you what it is that's going to happen, but at the very least, we're thinking of a climate that is different, and a climate that is different is not only just hotter or colder, whatever it is, but it is impactful on the economy, on diseases, on human activities, on everything. So it's an existential situation. Now, I'm going to refer to some of the position of people who have pushed back against our assessment on climate change, and this is sort of the purpose of this talk. And so in the previous administration, the government took the position that climate was changing, and so what? Okay, so it goes up, it goes down, and so right now it's a little bit up, but it'll just go down. And why are we so worried about it? I mean, we've had climate events way in the past where it was even much, much higher with regard to basically carbon emissions as well as temperatures. And so what's the big deal? And to the point where you have, EPA chief saying something like, well, climate is changing, but not only that, but there's no point in us actually worrying about it because we don't have a way to make really good predictions. So basically saying, oh, well, we need to study this more and we need to make responsible decisions once the science is settled. So indeed, climate is changing. So what you see on the bottom panel is the temperature record as reconstructed from various sources, but it's experimental data. And this is all the way down to about 600 million years ago. And sure enough, the temperature, which is the vertical axis, has some very, very high temperatures, particularly if you compare it to today's temperatures. So you see today there's an uptick, but basically it's much lower. And so what I'm going to do is I'm going to tell you that indeed changes are happening, but the changes that we've had today, that we're having today, are very, very different from those in the past. Okay, so the first thing I'm going to do is I'm going to bring up a little bit of math. It's a theorem actually, and I'm going to use this theorem to make a point. And the point is going to be the following: is that random processes change, and there's a theorem that sort of reflects the thinking of people who are climate denialists, who say, oh well, you have fluctuations, maybe even large fluctuations of climate. But, we basically eventually revert to some sort of mean temperature. So what's the big deal? And so if that's true, in other words, in mathematics terms, we say if this thing has a steady or stationary statistical distribution, in other words, if you make a histogram, that histogram is not going to change over time, then it must obey this theorem. And the theorem refers to something called records. So record highs and record lows. So those are called records. And it essentially says the following: if you have a stationary sequence or stationary process, meaning statistics that don't change over time, then the record highs or lows will essentially happen with a probability which is, roughly speaking, proportional to 1 over the amount of time since the last record, okay? So basically, records happen at progressively longer and longer times. And it is a theorem. And we know more about theorems, actually, frankly, than, in fact, anything else that we ever know. So what we're going to do is apply this theorem and say, well, if this is a stationary record, if these climate denialists say that, oh, we just have fluctuations, it's not a big deal, then then the data must obey this theorem. Now, oh, I guess I already said this. So what we're doing is addressing this business of climate has changed and it's always changing. And so now what we're going to do is try this out. So first I'm going to do is I'm just going to take my laptop and generate a random process, basically just sort of random numbers. And what I'll do is I'll plot them in sequence. And then what I'll do is I'll identify in black all the record highs and the record lows. And the thing that you kind of see here is that the time at which these records happen sort of grows progressively as time goes on. So this is what the theorem, this is a representation of what the theorem predicts. So now what we're going to do is try this out on real data. And so on the left, you see the little laptop experiment. And on the right, you have here, this is Moscow airport data. You can download it from the GIS site and you can play around with this data. And this is from the NOAA, National Oceanic and Atmospheric Administration site. And we play the same game. And so you see in black the record highs and in red the record lows. And clearly this data does not obey the tenets of the theorem. So basically it's saying that whatever this distribution is, it is not stationary because one of the necessary conditions is that it obey this theorem. So you might say, well, that's okay, that's just one data set. So what's the big deal? So we tried this actually on, I don't know, hundreds. I think it was 300 data sets. These are all just simply temperature records obtained since the Industrial Revolution, since about 1850 till today. And we tried the same sort of thing. The left-hand panel is not very instructive. It basically says we tried a lot of things. And on the right-hand panel, you see just a few of these examples, and they all have these sort of very typical shape to them that basically say that none of them obey the theorem. In fact, we never found any of these records that obey the theorem. In addition to that, as you can see, the record highs are more frequent than the record lows. That's not predicted by the theorem, but that is something telling about how not only is that the climate is changing, but that it's changing in a very specific way. So before I go any further, what I'm going to do is I'm going to make a distinction with what we call climate and what we call weather. So weather is the stuff that you see on the TV, you know, tomorrow's weather, but it includes also tornadoes, it includes snowfall and so on and so forth. And what we call climate is underlying, it's a much longer time scale version of the same dynamical system, namely the interaction of atmospheres, oceans, and the landmass. And it's at much, much longer time scales or much, much larger space scales. So you have basically weather that is riding over climate. And so climate we're thinking of in the terms of, you know, tens of years, 20 years, thousands of years, and so on and so forth. And weather is something more in the order of weeks, maybe a month, and so on and so forth. So what we're seeing here is weather, and the systematic uptick is something to do with the underlying process, which is climate. Okay, so one of the things that this is essentially predicting is something like this. So think of the distribution of temperatures, if you will, and you plot a histogram of this thing, and you do that, I don't know, 20, 30 years ago, and you have the previous climate curve here. then one of the possibilities is that the climate is shifting weather upward. And so as a result of shifting it upward, it's actually producing more record hot events than they are cold events as compared to before. Now, this is only a caricature of what's happening, but the shift of the mean is quite clear. The shape in which this distribution is changing is not so clear, but it is shifting the mean. So climate is changing, and it's changing in a very, very determinate way, not in the way climate denialists want to think of it. Okay, so that's one part of the supposedly learned argument from climate denialists. The other part of the argument is something along the lines of, there's too much sensitivity of our models are just not very good, or at the very least have many, many processes that we still don't understand. You're wasting your time using these things to make predictions. What we need to do is just simply stop fussing with this thing. Let's wait till the models are working properly, and then we can actually decide on what to do. So that's essentially the other part of it, is that there's too much uncertainty in the models and in the techniques that we use to predict climate. And so making predictions using this thing, the underlying idea is that it's irresponsible to do that with these kinds of models. So let's address that. So what I'm going to do is the following. I'm going to say, okay, fine. What I'm going to do is I'm going to take every known possible uncertainty that I can get my hands on, and this is from experimental data. And I'm going to take a very crude little model. I'm going to explain what this model is in a second. And I'm going to incorporate all those uncertainties into this model based on the uncertainties of the data, and see whether or not it's true that we can or cannot predict, or what is it that we predict in the first place. Okay, so let me explain what this little model is. I don't know if you're going to see my pointer here, but this is essentially it's called an energy bounce model. And the energy proxy here is temperature, capital T. And C here is the capacity, the heat capacity of basically of the whole Earth. Okay, so you think of this whole Earth as a single system, and it's being radiated by the sun. And you want to predict what the temperature of the global temperature is. You can use this balance model. And on the right-hand side, this term here, A plus BT dt, this thing here is the linear fit on the temperature of what is called the black body radiation. So Max Planck figured out that there's a relationship between heat and the radiation it produces. It's called the black body radiation. And so the temperature goes up and down depending on how much is absorbed and how much is radiated back. And that's this term here, the A plus BT term. Then the first term here, S here, is essentially the flux of sun, but we don't get all of the sun actually absorbed by the Earth. What happens is some of it gets reflected back into space, and the amount of reflectivity has to do with the clouds and snow cover and so on and so forth. And so 1 minus alpha is the amount of sun radiation that we actually take in. The alpha is the amount that gets bounced back. And that alpha term is roughly about 1/3. It's not very hard to actually estimate what that term is. The last term here, nu sub t, is a noise term. So I'm just simply artificially going to add, I'm going to clamp this down here, but it's essentially a random process. And every time you run this model, it's just going to generate different numbers as a function of time. And it's going to represent the variability or the uncertainties in this model. And I'm going to pin this down. And then finally, this term here, which is the term in which we appear, is called the greenhouse gas contribution. And Q is essentially, in terms of energy, is how much of the energy gets trapped in the Earth. And so I'm going to actually, this is the one that is producing all of the commotion. So this term here, now I'm going to parse that out, is composed of two components. So Q, greenhouse gases, is composed of something called the long wave component of radiation and the short wave component of radiation. And it's the sum of these two that eventually winds up contributing to what Q, greenhouse gases, is. So what are these two things? The long wave radiation is actually associated with the production of greenhouse gases, mostly carbon dioxide, but other gases. And the shortwave radiation has to do with volcanic eruptions, solar variations, basically. So these two components also have a component that basically makes the radiation of the sun change, and another one that actually emissions from the volcanoes actually will contribute to greenhouse gases, okay? Now, on the y-axis you see here is a watts per meter squared. It's essentially the contribution to this energy balance model. And on the x-axis here is time. And roughly about 1850, you see a big uptick in greenhouse gases produced by humans. It's in the order of, as you can see, 4 watts per meter squared, something like that. Now, if you take data and actually look at the shortwave radiation, volcanic and solar, what you'll see actually is a large portion of the greenhouse gases is, of course, that component, 240 watts per meter squared. And you can see fluctuations. Mostly these activities are mostly volcanic. And you can see basically that it is steady, not changing. Now, if you combine both of them, not surprising, you see the uptick still that occurs due to the greenhouse gases. Okay, so now what I'm going to do is run this model using all existing data. And not only I'm going to make sure that it actually agrees with our estimate of global temperature, but I'm going to actually make a prediction into the future and see what we get. So that's how we're going to play this game. So what I'm showing you here is 3 panels. And since it is a model, I can actually turn on and off certain things. And what I want to do is first, let's start with the bottom panel. And so in the bottom panel, the way you interpret this is the following. You see it goes from about 1850 all the way up to year 2100. So it's going forward in time. And in black is the data. So that is, I take all of the data around the world and I actually compose this noisy signal and I get this black data set, and that's the temperature of the world. And what you can see here is somewhere around 1960 or so, you have a very sharp increase, but the increase actually starts way before 1850. So if you go a little further back, you'll see that it's already showing signs of increase. Now, what these 4 different curves represent is different called scenarios. And the way climatologists work on these scenarios is they'll take different amounts of carbon dioxide and they sort of inject it into their models and make predictions as to see what happens. So these are sort of what if scenarios. The top curve, of course, is when you put a lot of carbon dioxide in the model, and the red curve is one which corresponds to roughly well, not putting all that much. Where we seem to be at is at the blue line right here. No, not blue, I guess that's cyan curve here. It's either the cyan curve or the next one over. That seems to be where we're headed at right now. And I'm marking here the 2 degree Celsius increase. And roughly speaking, we're going to hit that by year 2050, which is not that far away from now. Okay, so this is a prediction with all the uncertainties that we know about of this model. The model tracks data quite well, but makes predictions, and lo and behold, whether you like it or not, you see that the Earth is still warming up. Okay, so even though we have uncertainties in this, we can still see that. Now you can say, well, okay, so what is the part that actually is contributing the most to what's happening here? And so now we go back to the first 2 panels. And so what I'm doing here is including the man-made component, the anthropogenic component plus the volcanic side, and these are the predictions that you would get. So they track quite well, and then they start actually making big changes after I guess the year 2000 and so. And you can see that the volcanic component is strong, but it's not enough to actually explain whatever is going on. So basically the anthropogenic component is the strongest. Now, if you say, well, let's turn off the volcanic component, let's just simply include the anthropogenic and the solar, then what you get is this curve here. You see that the solar variations are not very impactful on the climate predictions. I'm getting a lot of, my phone is going like crazy. I don't know if it's because I'm getting, no one's in the chat. Am I missing something? If my phone is going off the wall on indicating that something might be happening. Okay, so I'm going to stop here, make sure that everybody's still with me, and ask if there's any questions at this point. Okay.
Maybe this is not, I don't know if this is a question you can answer. So that you have the noise term there.
Yeah.
How is that, how do you incorporate that term?
Okay.
Or...
Very good question. Okay, so that's the famous noise term here, right? So what it's doing is it's affecting the energy balance. And what we do is we throw this in artificially. We say, okay, let's assume that the model, the deterministic model is everything else. And we say, okay, let's actually artificially put in a noise term here. And what we're going to do now is build a model for this noise. And it's a fairly complex model for the noise. And what we do is we run the data, and the noise has parameters in it. And then we fit the parameters of the model based on the data. Okay. And once we are happy with how variations of climate, so basically, see all this noisiness, all this up and down business here that you see, all that is that particular term. It's tuned so that if you produce, this thing now is going to produce a statistical prediction, that statistical prediction will come as a member of the statistical distribution. You won't be able to tell that one from an element that you pull out at random from the distribution. So in other words, you know that you've done a good job if you cannot use any analytical means to tell which one is a real and which one is a synthetic sample from that distribution. And basically what it means is that the noisiness in terms of amplitude and frequency more or less looks the same. So, okay, so the data is the black, right, with all its inherent natural noise. And that one is used to generate all the other colored curves. And all the other colored curves, as you can see, have a noise that's very similar to the data. So that's how that's tuned. And we say that we are satisfied when we cannot be, we're not able to actually infer any differences between one and the other. Does that answer your question?
Yeah, thank you very much.
Sure. Okay. So the conclusion of this is basically the following, is that if we are okay with the data, and some climate denialists, of course, will say, oh, well, there's something wrong with the data, and they have all sorts of reasons to think there's something wrong with the data. If we think that the data is good, then we can use all of this data to incorporate all the possible uncertainties we can imagine into any climate model. This is a very simple little climate model, but we can do it in a very complicated model that's used on a supercomputer to do the same thing. And what we get is that the conclusions that the Earth is warming up still are correct. And secondly, that the rate of warming is no different. That is to say that you have variability for sure, but that variability is small compared with the overall trend, as you can see, of it growing. The other thing that I didn't show you in any detail, but this is something that happens, is if we remove the human element, the greenhouse gases caused by our activities, there is no way you can replicate the existing climate data that we know and speak of between 1850 and today. There is no way of doing it. Now, another thing that was pointed out by some of these climate deniers, especially when I went to Congress, is they said, well, you know, even if you incorporate that uncertainty due to greenhouse gases, especially from human beings, how do you know that is done right? And the counter to that is quite simple, is if there's something that we know fairly well, is how much oil consumption and energy consumption is used around the world. Why? Because it's a lot of money. So anything to do with a lot of money, we know fairly well. And so the argument that we can't pin down or clamp down very precisely what our contribution is flawed, because it would imply that we could not account for how much oil is traded and used and so on and so forth. The second thing that's amusing about this is that the people who are climate denialists will say also, well, you know, once we do study this thing, what we will do is we'll come up with geoengineering techniques to actually take care of this global warming. And so we just have to wait, and you'll see we're confident that human beings can work on this. And there's an irony to that, because if you're able to climate engineer the problem, you need to understand the problem and say that the data is correct. And if you understand and say that the data is correct, then you don't have an argument to say that we cannot predict climate. Okay, so so the takeaway is the following, is that yes, indeed, we all agree the climate is changing, but it's basically leaving modern era conditions. And because of that, then the weather will change. In the last few years, everybody's experienced or seen news events of you know, hurricanes happening much later in the year, tornadoes happening in places that never happened before. There was a few in Tennessee and in other places where these things would hardly ever occur, and they're happening more. Why are they more intense? Is because the well, it depends on what it is, the hurricane or tornado. For example, for the hurricanes, the ocean is warming up, and because it's warming up, then the ocean is the heat engine essentially for the hurricanes. It's the energy source for these hurricanes. It is becoming able to produce more intense hurricanes. The other conclusion is that the warming trend forecasts remain unchanged even when uncertainties in natural and anthropogenic effects are accounted for. And therefore, even though these models have errors in them, we can still make predictions on which one can base policy. And the other thing that comes out of this thing is that the Earth's climate will not be able to be replicated unless you include the component of human activities. Okay, and so what I'm going to do is I'm going to stop there, actually. I'm not going to go much further than this. I'll tell you who my co-author is, Michael Mann from Penn State. And I'm also putting a few articles that are easy reads. You can download them and you can read them for yourself. And what I'm going to do is I'm going to stop with that and just open the floor either to talk about climate or actually also talk about careers in science, which I'm also keen on talking to you about. Okay, so I'm going to do the following while I sort of address questions on the climate issue. I'm going to see if I can open up my other presentation, which has to do with Oak Ridge itself. So if you will, just shout out your questions and I'll find my presentation. It's on the other computer, of course. Let me see if I have it here. Well, I can do the following. Yeah, it's on the other computer. Let's see if I find it here. No, it's on the other one. Okay, so I'm going to do a little switcheroo on computers. and open that. But why don't we open the floor for questions at this point?
Okay, I have a question.
Yeah. Mhm. Yes.
Is this damage that we've caused to the environment reversible? And if it is there a point where it will become irreversible?
Yeah, so the answer is yes, there is a point at which it can become irreversible. The way we more or less think about it is whether or not it basically amounts to the following. Using existing technology, and this is by way of doing conservation or using alternative sources of energy generation, can we actually bring down the temperature to a level which we can tolerate? And the answer is that if we keep the temperature growth from reaching that famous 1.5 degrees Celsius by 2050, then our existing technology is able to bring that down. It'll take a while for this to happen, but it's possible to bring it down. So now, of course, by 2050, there might be technologies that will be available that might be useful in bringing it down in other ways, but that's how you should think about it. So using existing, the other thing that comes into these things is the economic part. Let's say, well, do we have the amount of money required to make that change, right? And those arguments then no longer are scientific, they're more of a political or economic. In the following sense, you might say, well, you know, it's going to cost so many trillions of dollars to put together, to replace all of the, you know, carbon-based fuel energy sources. Fine. And then someone would say, well, if we have that much money, why don't we, I don't know, let's say cure malaria in Africa? Why don't we cure cancer? Why don't we? So there are all these things that become more pressing and more important than these sort of things. And so that becomes now the realm of climate change as economists or sociologists think about it, right? So that's how you should sort of think about this. Now, so what's going to happen? So we're not going to reach, I don't think we're going to be able to reach this 1.5 degree by 2050. Not the way things are going right now. We might be surprised. But if we don't, it means that it's going to take a lot longer for us to come down to a level below 400 parts per million. And what the impact of that is that during that coming down, it's a long time, there's going to be a major shift in the economy. It might be, for example, that Iowa is no longer the breadbasket of the world, for example. It might be that there's going to be lots of diseases and so on and so forth. So it's a major shift on everything that we do, right? So that's how that works.
Thank you.
Sure. Okay. So keep asking questions because I'm struggling here. I got you know, so working now for a laboratory means that there are certain security protocols that one has to have for things. And so I have to shift computers here. So please ask more questions. Also ask questions about if you're interested in careers in science or what have you. I can address those too.
Okay, I'm gonna let the students keep thinking about questions, but I have a kind of a mathy question.
Oh, good. Okay.
Sort of. So the model you showed is a relatively simple model, right? It's a first, is it first order? It looks like a first order.
Yeah, so let me, okay.
Yeah,
let me bring that up
and I mean, I know I have seen other climate models that are like you said, they require a supercomputer. You know, they take many inputs and highly complicated. This is not one of those highly complicated models. So my question is, I have seen the output of the highly complicated models and it looks pretty similar
Yes.
to this one, right? So can you weigh for me why you would use the one you know, what different information are you getting from the one model and from the other? And, you know, because the computational cost of the very complicated one, what benefits does it give you over the one that isn't?
Well, that's an excellent question. So let me do the following, which is share my screen again so that everybody knows what we're talking about. Okay, so here's, hopefully you see this. I'm just putting back this model. Okay, come on. Okay, so there it is. All right. Okay, so again, this is just simply telling you what the temperature is at any given time, right? Little t is time, capital T is temperature, and capital T is a proxy for the amount of energy. Now, okay, so the whole thing is scaled by in units of watts per meter squared. Now, it does a remarkably good job at recreating the data, as you saw. And the question is, well, if it does such a good job, why do we need all these supercomputers and big models and so on and so forth? What is it that these other things bring in? And so the answer to that is, it's got two parts to it. So one of them is the following. This particular model will tell you something about the global temperature, right? This temperature doesn't exist in the real sense of you can go and measure it. What you would have to do is you would have to take temperatures from all over the world, data from all over the world, and actually recreate what this global temperature means. But essentially, it's a statistical averaging process, okay? So it's going to tell you about the whole world, right? And it won't tell you what happens at each individual location in the world. So one reason for having these big models is because we're interested in knowing how specific parts of the world actually will fare in different climate scenarios. The other reason for this is the following. This particular model is essentially driven by data, and it's tuned to data. Now, the very complex model is initiated with data. So you clamp it down at a certain time and place. You sort of say, okay, let's take all this data, clamp it down, and then you run it freely, right? And you let it do whatever it does. And so there is still tuning in these big climate models. There's no question about it. And they agree with the outcomes you have here. But the interesting thing that you see from these big climate models is now you see processes that are causal insofar as what exactly happens. So for example, you don't have an ocean here or an earth, an atmosphere or a landmass to tell you what is doing what. One of the interesting things, I work mostly on ocean transport. And so one of the interesting things in climate is how important the ocean is to climate. And one of the more famous or infamous events that can happen in the ocean is that there's a very slow overturning of the ocean that essentially modulates the temperature. After the sun, it's the most important component of climate. And the climate that we know and love depends on something called the meridional ocean circulation or thermohaline circulation. This is very slow. It takes about 5,000 years for a little clump of water to go from New York City back to New York City again, but it sort of rides around the world. And this is sort of a river, if you will, and it's a conveyor belt for sinking carbon dioxide as well as temperature. Now, what can happen is if there is a severe warming due to carbon dioxide, what can happen to this particular river is it can stop. And this you get from a big climate model. You see it actually will stop. And if it does, then you'll have a runaway situation, a runaway climate. You will never see that from this little model, but you do see it on these big models. So the short of it is this, that the big models and these agree with each other. They have the same sort of underlying physics, but the bigger ones will tell you spatial temporal predictions and causal issues that one can actually study and analyze and figure out. And it also will tell you something about what happens to your weather locally. Okay, I'm gonna stop sharing again. And I'm still working on getting this talk going. Let's see, so I think I found the presentation. Okay, now, so let's see. The only way I'm going to be able to do this is if I log out and basically log back in. Would it be okay if I do that? All right, so I'm going to leave and I'll be right back. Just hold on.
I know there has to be student questions here. Come on. Somebody asked her about his path from music to physics, you know, like, he needs to ask that. So I've already asked.
Sorry, I'm back, and I have not so good news, which is the computers are not letting me. We have a sort of a security lockdown due to political circumstances elsewhere, and I'm not allowed to bring up this talk. But let's improvise. I'm a musician, so I know how to improvise. So what we're going to do is the following. So first of all, I'm going to improvise, try to answer some questions on things like either careers in science and or opportunities at Oak Ridge. But the other thing I'm going to do is I'm going to promise everybody that I'll come to the university and I'll talk to everybody. We'll have lunch together and we'll talk informally about all sorts of things. And so I'll make sure I make that arrangement, and we'll do that sometime in the next couple months.
I will be sure to work with you on that. And kind of a segue from what you just mentioned, talk about improvising. So what caused you to switch from a career in music ultimately to going into climatology?
Well, okay. So well, there's an amusing story. It's more colorful than the version I'm going to give you. So when I see you in person, I'll give you the more colorful version. But so I come from a family of artists. My mother's trained at Juilliard. She's a professional pianist, and my father was an artist, a painter. And so our notion of rebelling was to not do art, but I was trained as a musician since I was a little kid. So I said, oh, I'll just go do music. By the time I went to music school, I was so sick of working as a musician, I started hating music. Not only that, I hated my life. It was just terrible. And I was working, but I just didn't have much pleasure from it. And sometime one night, I remember I just got so frustrated. I said, you know what, I'm going to go into this really hot summer right now. This thing of going to audio recording is not doing it either. I'm just going to go back to school for a vacation. So I enrolled into graduate school at Columbia University for electrical engineering. Why electrical engineering is because my double major in college was music and philosophy. And so I knew everything about existentialism and death and all that German horrible philosophy. And I thought, okay, I'm sick of people and music and everything. I'm just going to go study engineering, not knowing what the hell I was getting into, just because I thought it would be amusing. So that's how it started. Now, I did have a fairly good preparation as a high school student in science. I didn't go to high school here in this country. I went elsewhere. So I was quite well prepared. And then I tried electrical engineering. I met Cyril Harris. This is an acoustician who actually did the Lincoln Center Acoustics, the Kennedy Center in Washington, and so on and so forth. And I thought, well, maybe I'll do acoustics since it's somewhat related to music. And but then I just got fascinated with this sort of idea of waves that just threw me to no end. And I said, well, where do I study things that have to do with waves? And at the time I was a graduate student, there was a big fascination, there still is a fascination with something called a solitary wave. And a solitary wave, the most famous solitary waves that you would know about are tsunamis, but these also happen in condensed matter physics and so on and so forth. And so Cyril said, well, why don't you just go study physics? And so I did. And so I said, well, I got nothing to lose. I'm just taking a vacation. I'll just go back to being a musician. And then the long story is that I started loving science more and more. And I thought, I'm just leaving this music behind. The upshot of this is the following, is that because I had nothing to lose, I had nothing to prove, and I wasn't scared, somehow I was able to go through this process. I just found it challenging, but better than working for a living, and so I had an easier time with that transition than if I had decided, oh yes, this is what I have to do. I didn't have these pressures. And it sort of happened naturally. And so when I talk to students, I tell them, look, if you're freaking out or something like that, it's time to do some evaluating. The other thing that happened is I had a lot of music score paper around, lots of it. And I didn't know what to do with all this music score paper. And so what I would do is I developed a system for learning things, which I use with my students. Very few of them take me on for this, but I still believe it's a good system. So on one side of the notebook or whatever it is that you're going to use, what you do is you're going to try to replicate results that you read in a book. And on the other side, you're going to immediately write down questions as to, well, I don't know how to go from this step to this step. What is this? And so on and so forth. And you immediately write these down. Now, there is also a process of going through a book. So first, I don't read a chapter. Forget about reading a chapter. I just go straight to the examples. There's a reason why those examples are there. And I start working through the examples, even if I don't know what the hell this is all about. And I try to replicate all the steps in the example, making notes as to, okay, I don't see how I can go from here, here, and here, here. Then what I do is, and make notes. Then the next thing I do is I go to the exercises and look for the simple exercise at the end of the chapter. And I see if I can do those. And then I read the chapter and not before. And what happens is you wind up learning that way as you would learn a sport. You don't read the book on sports, you start doing things and you kind of get sort of the hang of it. And only later is that you say, okay, now I have to really be good at this sport, right? And the same thing would go for music, right? You start playing something and then, you don't start with a Beethoven symphony, you start with just messing around on the piano and slowly but surely work. So I personally think this is a very easy and organic way to learn. It's not the most efficient one, but it really is effective. And I was able to make that transition from, I don't know, music composition. I was taking partial differential equations in 6 months. Then again, like I said, working for a living sucked. And so I was happy to be going to school. I was thrilled to bits. And then, the other thing I do with that list, I forgot to tell you what I do with the list. So I have that list and I start crossing out things that I'm confident that I already handle. But things that I don't, I just go with very specific questions to people. And I say, I don't know how to do this. And I'm not leaving this office till I figure that out. And so you just sort of knock these things out. And so by the time the exam came around and everything, I was pretty sure that I knew how to do everything because either I taught myself how to do it or someone just told me how to do it. And it was as simple as that.
Thank you. Do we have any questions from any of the students, any of the other audience?
Trying to see how many students do we have here? Yeah, quite a few. Yeah. How many of you guys are so I don't know what my audience is. Is everybody in science, or is this everything? Everybody's in science. Is everybody in?
I'm
Sorry?
not sure. At the peak, there were almost 60 people here, and most
Yeah,
of
no,
them
this
were
is
students. So, yes.
yeah.
How many of you, can you raise your hand if you are a student in natural sciences, so biology, environmental studies, chemistry, biochemistry?
Okay.
All right, how many of you are in the division of math, computer science, engineering? So I don't know if you can see kind of by show of hands.
Okay. So
Some of them are in my differential equations class, so thank you for putting that up there.
oh, there we go. So in fact, I'll give you a link to that. You can put it up in your class and mess around with it. There's even a MATLAB code you can play with if you want to. Yeah, it's kind of fun. Most of you are basically sort of a natural science, environmental sciences, and so on and so forth. So I'm going to try to see if I can drag one of my colleagues from Oak Ridge to come with me to campus, and she can give you some ideas as to both careers in these fields and also opportunities at Oak Ridge. So I'll make sure to do that so that you folks are covered. I will tell you that you should, all the students should take internships. It doesn't matter even if they're not exactly what you're looking for, but every undergraduate should have an internship in a laboratory or even a corporation or whatever it is. This is extremely important. And don't worry too much about it being exactly what you're looking for. Oh, I'm a mathematician, I have to do something in mathematics. It could be in physics, it could be in whatever it is. And I can tell you a little more about that, but basically the upshot is that this internship is not only a good way for you to find out whether or not this is a career for you. You can even try something you didn't want to do. You say, hey, I'm in mathematics, but I want to see what medical people do. And so you just do an internship in a hospital, right? But working closely with someone is going to give you one of the most important letters of reference that you'll have, and more important than, frankly, than your most of your faculty, and certainly more important than people have little connection with your future career. So look for that internship. You learn skills that you don't learn at school: responsibility, communication skills, so on and so forth, sort of the soft skills that people say. You get one of the most important reference letters, and also just a really good experience. So by all means, look for these things and look for people who can help you get these things. Other questions?
I have another quick question on the climate issue.
Mm-hmm.
Are there any ways you could use a biochemistry discipline to sort of undo the effects that have been done?
Yeah. So I have a project right now. It's a two-part project. So this is a project on studying what are called geoengineering climate remediation. And geoengineering includes biological methods and so on and so forth. So it includes everything. But the idea is there a way for human beings to actually make changes on something to regulate climate? So one project has to do with studying in general the issue of policies in geoengineering. And I'll tell you in a second what comes out of that. And the second one has to do with understanding, and the one I'm working on here at Oak Ridge, has to do with understanding systems biology. What we're trying to do is trying to come up with ways of inoculating, if you will, plants to severe stresses. So there's anecdotal evidence that if you stress a plant, for example, pre-stress it, let's call it, that it's able to handle stresses later on, much more extreme stresses. And so that's seen as a very cheap way to inoculate a plant. You can do it by pre-stressing using biochemical means. You can use other means, but right now we're working on the most simple ones, which is just water and temperature, right? So heat up the plant or whatever it is. But there's another group working on the biochemical route, on the biomolecular route, is to either, more conventionally genetically engineer something or change the regulation mechanism of photosynthesis to make a plant more resilient to change. So yes, so that's the sort of things that you would wind up doing, in addition to finding alternative sources of fuel and so on and so forth, biofuels and so on and so forth. On the first one, so we were supposed to look, I was looking at whether or not geoengineering was a feasible way to change how climate would go. And the answer is yes, you can. But the more interesting finding there is the following, is that once you start messing around with Earth's climate, you will always have to mess with it. There will be no longer ever a natural climate. So once we start messing with it, we're stuck with it. And we have to change whatever it takes, we have to now regulate it. Now, that sounds a little shocking and a little tremendous, but we've already done that with certain things. Like, for example, we cannot live without antibiotics, for example, right? I mean, so this is our human, humans just, we rely on antibiotics. For all that matter, even shoes, for crying out loud, right? So there's no way we can do what we do without wearing shoes. We are stuck with wearing shoes for the rest of humanity, kind of thing. So it's scary on one hand that we're thinking, well, if you mess around with climate, you always mess with it. But on the other hand, it gives us the only option for doing something when things really go berserk. It doesn't tell you what to do. It just tells you that if you start, you have to keep doing it.
Yeah, thank you.
Mm-hmm.
Okay, are there any last questions from our students? Mackenzie, you popped on, popping off.
I see lots of, well, thank you everybody for showing up.
Yeah, a lot of our students have a class at 1, so they had to run to class.
Well, yeah, I've spent 30 years teaching, so I know how that goes.
Well, thank you so much again. This was great talk, I think.
Absolutely.
Been talking about it for a while, and as soon as we can have you here,
yep.
Just say the word and we'll make that happen.
Yeah, I would love to. And I'm new to Tennessee, but I saw your campus. It's very pretty. So so I'm looking forward to.
We are nestled in the foothills of the Smoky Mountains. So
yeah, that's right. All right. So I'll be sure to bring my student presentation, and I'll see if I can bring a bio person of some sort or another, my collaborator maybe in systems biology, and we'll come and visit and have lunch with you guys and the students.
Great. Thank you so much.
Of course. Great meeting, everybody.
Great to meet you. Thank you.